The game of hex was invented by Danish mathematician Piet Hein in 1942 and reinvented in 1948 by Princeton mathematician John Nash.
The game is played between two players on a hexagonal grid. Player 1, indicated by blue, attempts to mark individual hexagons to construct a path from the left to the right sides of the board, while Player 2, indicated by red, attempts to construct a path from the top to the bottom of the board.
In 1949, John Nash proved that a game of hex cannot end in a draw, which is also called the hex theorem. Now consider an example. First, imagine a rhombus shape, bounded by a wall at its top and bottom, in which a river is flowing from left to right. Imagine that the shape is tilted at an angle, where if the river is obstructed by an obstacle, the force of gravity allows the river to flow around the obstacle. Now construct a small dam to stop the flow of the river. The river will simply flow around the dam to reach the right side. Thus, the only dam that can prevent the river from flowing from left to right is one that perfectly extends from top to bottom.
Now consider a condensed hex board in which every hexagon is marked with either an X or an O. Let player 1 mark hexagons with an X and let player 2 mark hexagons with an O. Mark the northwest and southeast sides with an X and X prime, and mark the northeast and southwest sides with an O and O prime. Now mark each boundary between either adjacent hexagons marked differently or between hexagons on the boundary of the board marked differently than the respective boundary. Consider the shared vertices between each hexagon within the board as nodes. There'll be 4 nodes at the 4 corners of the hex board with degree 1. Now examine the previously marked boundaries. They have created 2 paths extending between the 2 adjacent nodes of the 4 nodes. Given that the paths do not intersect, they will trace out a winning chain of hexagons. Thus, for any configuration of the hex board, a winning path for one of the players will exist.
Recall the example in which one copy of a number line was folded and then placed over another copy of the number line. The same phenomenon would occur in 2 dimensions when holding a high-point map if you are at any location on campus. There is some point on the map that lies exactly over the point it represents. This extends into the Brouwer's fixed-point theorem. Suppose X is a topological space that is both compact and convex, and you let F be a continuous map of X to itself. Then F has a fixed point in X, that is, there exists a point X star in X such that F of X star equals X star.
Before simplifying this, we need to define a few terms. First, a space that is compact is closed and bounded. Consider a circle graphed on the coordinate plane. If the set of the points contained within the shape includes the boundary of the circle, then it is a closed space. Likewise, if the absolute value between the 2 arbitrary points on the shape is less than a given value, then it's bounded space. Finally, in a shape that's convex, any 2 points within it can be connected by a line, and the line will remain entirely within the shape. In examining these 3 shapes, the rightmost shape is not convex, given a line can be drawn which connects 2 points within the shape, yet passes outside of the boundary of the shape. Now let us simplify the definition of Brouwer's fixed-point theorem. If a space is closed, convex, bounded, and continuous, then there will be a point on the new space that maps to itself, hence the point stays fixed.
We can use the hex theorem to understand Brouwer's fixed-point theorem and vice versa. First, we can prove Brouwer's fixed-point theorem through a proof by contradiction. Assume there's a way to manipulate a shape in space, for this example a hex board, so there is not a fixed point.
First, take these identical number lines. We can non-violently deform the second one in any way and lay it on top of the first one. Then, we'll draw arrows from each point's starting position on the first paper to its ending position on the second paper. This will result in many arrows pointing in all different directions. Take these arrows and put them on a hex board with teeny hexagons. Color each hex based on the direction of the arrow. So if an arrow was pointing left, then we'll color the hexagon blue. After shading in all the hexagons, there will be a path from one side to the other because of the hex theorem. Look at the east side. Since the hexagon is blue and on the edge of the board, the only direction the arrow could be pointing is left. As you follow the line of hexagons going west, the arrows will all be pointing the same in the same direction. But then look at the west side. Since the hexagon is also blue and on the edge of the board, the only direction the arrow could be pointing is right. As you follow the line of hexagons east, all the arrows have to be pointing in the same direction. This is a problem because coming from the east, all the arrows are pointing left, and coming from the west, all the arrows are pointing right. This means the arrows have to be going two directions at once. This is impossible. Therefore, there must be a fixed point. So now you're probably wondering, how do I win the game hex consistently? Well, unfortunately, if there is a book of all possible hex strategies, the book would not fit inside our universe. We can, however, conclude that there is always a first player winning strategy. Assume player 2 has a winning strategy. On the first player's first turn, they can place a ghost tile anywhere on the board. This allows them to steal the second player's strategy by forfeiting their first move and becoming the second player. If the game was to be continued as normally played, the first player would eventually come back to that originally placed ghost tile, almost seeming like a double turn. Therefore, the first player always has a winning strategy and the second player cannot have one.
That was actually pretty good. That was pretty good, right?
That wasn't